I'm Yassine Khier, as Omnia introduced, and I'm a second year PhD student. And mostly I'm working on audio defake detection with the speech and language group at the German Research Center for AI. So I know you all that you know the rise of generative AI, and that's everyone know it's using AI for to generate contents or to use it like for different things. So basically, this generative AI models refers to models that can create content in general, like for example, images, videos, or audio, or even text, like ChatGPT. It's a generative AI model, but we are not interested in that for now. We are just interested in Gen AI that can create contents, for example, images, videos, and audios. So we know that all these models takes as input a prompt. Maybe it can be just a written text or like an image as well as a prompt, and then you can ask it to do something, to change it to some different features, or like to make it like a art, or like to generate a video from scratch, to do marketing, whatever, or like to generate audios as well, and it will do it straight away. So we've seen this hype, especially starting from 2020, but it went to the public really viral in 2022 and 2023 as well. And the market projection, it's more than $150 billion by 2030, which is huge. Actually, this Gen AI, it's very useful because it's revolution, it helps in many industries. For example, the creative industries, marketing, film, education, accessibility tools. Just yesterday, I've seen that the Oreo, the company Oreo, they trained their own video generative AI models so that they can create some marketing videos, which is huge. But the problem, like for example, just as a real example, so my picture in LinkedIn, just instead of spending 25 euros so that I can get a professional one, I just use Gemini, Banana, and then just prompt it to get a better a profile picture. So that's also good. And you can use it for that. In terms of speech, we have as well Gen AI speech, as you will be aware of that. And usually we call them speech synthesis. And they can be classified as two different models or different pipelines, TTS, text to speech. So these models takes as input text and output speech. And usually, previously, like before 2020, it was usually a pipeline trained with one speaker. So we have one speaker reading, for example, 20 hours of speech. And then we train a model, a TTS model, so that it can replicate the same speaker given a text. And there were as well like other models, which are voice conversion. So basically the voice conversion, we get as input two audios. So you get a source speaker and target speaker. And basically you have a source speaker that has the content that the target speaker should say. So for example, let's say that I am the source speaker and the target speaker is Omnia. So I'm the source speaker. I can say a sentence, hello everyone, how are you today? And the target speaker can be Omnia, and I will take any short clip from Omnia saying anything. And then the voice conversion, what will do, it will just make Omnia say, hello everyone, how are you today? So it will just kind of force Omnia's timbre and voice to be replicated on the same content that I've said. And this is very, like nowadays, it's very easy and very accessible to anyone. And the trend now, it's not even to have like two different models, TTS and voice conversion, but in a one combined model. So a model that can do TTS so that it can take the text and output the speech, but at the same time can do the cloning. So can take the text with the target speaker and it will output like the content in the target speaker with the content that you write in the text. And nowadays it's very accessible, so you can go just to Hugging Face and you will find plenty of open models in different languages. Maybe dialectal Arabic, it's still not really good, but you can find plenty of languages. So for example, like I did this pipeline in maybe less than 2 or 3 minutes to generate audios. So for example, here I have a sentence. Last month we reached a new milestone with 2 billion views on our YouTube channel. I just use Chatterbox and I get this output. Sorry.
Last month, we reached a new milestone with 2 billion views on our YouTube channel.
And it sounds really natural, like a human saying it. And it's really easy and accessible to everyone. So, and the same model, the Chatterbox can do the voice cloning. So basically we have this voice that we generated, and I took one utterance of my voice, speaking in Arabic.
السلام عليكم ورحمة الله تعالى وبركاته كيف حالكم؟
So it's really completely different content and different language. And Chatterbox can even tries to replicate the same content here with my voice. It's not really close, but sorry.
Last month, we reached a new milestone with 2 billion views on our YouTube channel.
It makes a bit my accent a bit Indian, but it's no problem. But at least we can see from here that the pipeline itself, it's easy and it's accessible to everyone. So, but the problem here is that these synthetic voices or like these synthesis methods, because they are accessible, they becomes a weapon. So they can be easily misused in different scenarios. So for example, voice impersonation scams. So for example, I can just replicate Omnia's voice and then make some announcements in the university and make some announcement to you and you will believe in it. Some political misinformation that's happening a lot, especially during the elections. So basically, you will create some different statements. For example, Trump saying something very, very, very different, and then you will publish it. Or for example, like for the financial cases. So for example, you will drop. For example, if I just replicate Elon Musk's voice saying that I will buy this one, like. So I will influence the huge market with a fake sample. So like social engineering and vision attacks, as we can see in different social media things, and fake media and artistic defects. Basically, we can see that hugely in the pornographic content, and that has hugely increased like during the recent year, according to reports. And according to one of the real-world examples using these deepfakes as weapon is what happens in 2023. So a voice clone was used to steal around $35 million from a Hong Kong company. So a CEO voice was cloned, and it was used to pass an order of $35 million, and that was just recently in 2023. The same thing happened in 2024 with these robocalls imitating US politicians so that they can influence the fool. So they can vote on different politicians. And yeah, so we can see the misuse, and we need to address that. So basically, we need to have a countermeasure so that we can we can use this like these Gen AIs to generate content to like use it in our life, but we need as well another AI model that can tell us whether an input speech is it real or fake. So that's why we need such kind of models. So basically, we know in general that AI models can take prompts and generate really nice content. So AI learns from pattern and are very robust, as we can see from ChatGPT and like VO3 and all these models. So why not using AI itself, but in this time as a defender? So instead of generating content, it will take the content and it will act as a defender and say whether the content is real or fake. So basically, as you would know, that to train such systems and to train these AI models that can do such tasks, we need two things. The first thing is that we need the data, so a huge data, that has the content and the labels. So we know like different contents, like we will collect different audios, videos, like images, a lot of this, and then label them. So for each content or for each wave, we will have two labels, whether it's real or fake. Like for the first part of the modeling side, it's easier because like as I said, in Hugging Face, I can go and like within minutes, I can generate thousands of files that are fake, and they can get from the internet or from YouTube thousands of samples that are real. So to generate the data or like to construct the data, it's very easy and like it's very cheap. The problematic part is that how I can model this. So how I will construct the AI model to do such thing. So here it comes the question, which AI models are most suitable to do defect detection and how we can optimize their efficiency. So basically, we don't like the decision should come in very short time because like if I have a content, I want to verify it, I shouldn't be waiting for 1 hour or 2 hours to verify it. It should be like quick. So I need very small models and very efficient models. The third thing is that will they generalize effectively? Because nowadays we can see like every day we see new models, new Gen AI models that are there and very different from each other. So the model that we're gonna construct, it should be generalizable to all these kind of defects. So that's what I will try to show today. Especially, I will focus on the modeling side and how we can optimize for the efficiency, with their efficiency. So basically, let's go back to our pipeline again. So we have the audio that can be real or fake. Then we have the AI model defender that will tell us whether the audio is real or fake. So let's go and actually dissect this model and see in what ways we will construct it. So basically, we would like this AI model to have two main components. Just take it as a kind of a front end and a back end, like a feature extractor and a backend classifier. Basically, what's the terminology here? So basically, feature extractor, it will listen to the audio. Just imagine kind of a forensic agent, or someone working with the FBI analyzing the audio. So this feature extractor will just give us all the features that are there. For example, it will say, okay, the gender, it's male, it's not changing, the tempo is this and this, the phonemes that has been said this and this. So it's kind of, it will give us a report of what has been said. So it's kind of a police, like we are in a like police chief officer or whatever, and then all these features should be listed, including the age, whatever, like all the features from the audio. And then this report will be given to the backend classifier. So the backend classifier is kind of let's see it as an experienced chief officer that will see all the report, but it won't use all the points that you mentioned in the report. For example, I want to be like interested in knowing the age of the speaker to detect whether it's fake or real. But the backend classifier, it will list all this, it will see all this report, see all the features there, and will decide which features to use and which features will help in detecting the real and fake. So just to summarize, the AI model, we want to construct it in a way to have a feature extractor, kind of an agent that prepares the report for the expert, and the report should contain all the information about the speech that was given as input. Second thing, this report will be given to backend classifier, which is the expert. And the expert will analyze the report and will decide whether the sample is real or fake. So let's see here what we will be using. So I've seen a lot of like Omnia's previous talk, and I've seen that a lot of previous presenters they showed SSL models, which are supervised like self-supervised learning models. So that's why I wanted to bring up this subject and bring up especially the paper where I introduce SSLs for defect detection. Basically, we know that SSLs are trained on millions of hours of data, and they give really rich features. So basically, what they give. So given an audio, they will give, these SSL models will give a full report of different things that are there in the audio. So it will give the gender, the age, the phonemes that has been said, the transition between phonemes, F0, F1, F2, like all these kind of features, it will be given by SSL. So we can use it actually here, but how we will use it? Should we use it in the backend or the feature extractor? Basically, for the backend classifier, it can be just a simple classifier because it will look to all the features and just decide and it can be data related. So it will just adapt to the data and see which features are most useful and it can be used. So the backend classifier, usually we use backends that are that are less than 2 million parameters, and we don't have any problem with this. But the problem is the feature extractor or the feature extraction. We don't have really rich feature extractors that gives the full report to the backend classifier. So that's why we can use the SSL models for that. So we will give the audio, the input audio to the SSL model, get the report, and the report should be given to the backend classifier to decide whether the input is real or fake. Among the SSL models that we can use are Wave2Vec. It has been presented just last time. And Wave LM, Hubert, there are many different models that has been trained with thousands and millions of hours of data, so we can use them. But the only problem with that is that the feature extractor itself, it's very huge. So this SSL model gives a huge report. It's a model with 90 million the least to 2 billion parameters. It's a very huge model, but the task itself should be really easy and should be very efficient and quick because we need quick decisions. So SSL will give us a really good report, but the problem is that these models are very huge. So here we will be working, or I will be presenting a way to make very efficient SSL models for the task of deepfake detection. I hope I'm clear till now. So the problem here is that هنا عندنا هذا الريبورت الكبير. يعني we have 90 million, 300 million ولا 2 billion parameters model that will give us a huge report. But do we need all this report? Do we need all the features? As Tuqa said, so we don't need, for example, we need the intonation and the prosody because they will help us to detect the defects. But we don't need, for example, all the time to get the phoneme sequence because usually the phoneme sequence is correct. We don't need to get the gender because the gender is always correct or it will be always correct. We don't need the age. We don't need a lot of features. So we can get rid of these features and keep only what's necessary. So here where it comes the efficiency, and that's what I will be talking about. So let's come back to the feature structure. We talked about SSL, and here is the structure of SSL models. Basically, SSL models takes the inputs, the speech. So we have the speech here, and then we have some CNN layers to extract features. Then after that, we have layers of transformers. And basically these layers of transformers, it's kind of, each one of them encodes, like they encode all of them the same information or like kind of the same information, but some of them correlates a lot with some kind of information. So for example, if we go to the layer 24, we will find that this layer correlates most with words. With the layer 23, we will it correlates with maybe phonemes, Like I'm just saying, like it shouldn't be accurate. Like we will go to the transformer layer 9, we will see that it correlates a lot with the accent itself. So we need, instead of using all these layers, so all the reports, we need to be selective. So instead of using the 24th layer, we will be just using maybe 3, 4 layers, 6 max. So here we come to 3 questions. What do these layers encode? So we need to know what these layers have as information or like correlates with information. This is the first thing. The second thing we need to know, do we need all these layers for deepfake detection? Should we use all these layers from SSL models, or should we limit ourselves to only 1 or 2 or 5? Like how many layers should we be using? And is this behavior consistent across setup? So for example, let's say that for a data set, we found out that using only 6 layers is optimal. Is this like generalizable across different setups? So the same setup, or like using only six layers, will be the same will be giving me the same results if I use a different data set, a new model, uh, like different setups. So that's what we will be answering. The first, second, and third question. What do these layers encode? Do we need all the layers for deepfake detection? And the third thing is this behavior consistent across setups? So let's go to the first question. For the first question, actually, we don't need to answer it because it has been answered previously in a paper called Layer-Wise Analysis of a Self-Supervised Speech Representation Models. And basically, in this paper, they analyzed all layers and they showed the correlation between different tasks with different layers. And what they showed, that the lower layers, basically, are mostly acoustic. So basically, it encapsulates information about the prosody, intonation, F0. It has all this information. And the upper layer, so for example, here we can see from 6 to 12, they are mostly semantic, kind of having phoneme sequence. They know about phoneme sequence. They will know about the word alignment, and all of that, which is not very acoustic. And we can see it clearly here. So for example, here we have 2 models, 2 SSL models. This is wave-to-vec large. It has many layers. And this is wave-to-vec base. It has 12 layers only. And here we can see the tasks. So for example, here we have the local acoustic features. And we can see here the correlation. So basically, the correlation is very high in the lower layers. So basically here we can see layer 1 has a correlation of more, like 99% correlation, and it's going down. So the upper layers, they don't have really a huge correlation with acoustics. But whereas, like if we see the phoneme and word embeddings, we can see a huge correlation coming up in the upper layers. So the huge correlation is coming here, 7, 8, 9 layers. So that's give us a hint, actually, because like in defect detection, we said that we are mostly interested in the acoustics scenarios or acoustic features than semantic. We are mostly interested in knowing the prosody, intonation, F0, F1, all these statistics and all these features, instead of knowing whether what has been said, like the phoneme sequence or the word sequence. So that gives us a hint that maybe we can just use 6 layers instead of 12, or we can be using only 12 instead of 24. So we can limit ourselves to the number of layers. So how we will do that? So how we will verify that's actually using only small layers, or like only the first 6 layers or 10 layers is largely sufficient. So what we will do, we'll do this experiment. So basically we will take SSL, and from each transformer, take this as a small report. So transformer 1 is given a report, transformer 2 given another report, transformer n is given another report, but each one is different. So for example, transformer 1 is giving me more information about F0. 2 information about prosody or report about prosody. N is a report about like 24 reports about the phoneme and word that has been said. So I will take all these reports, and each one of them I will give it a weight. So basically here I will tell the model, okay, take this report from transformer 1 and give it a weight from 0 to 1. Same thing for transformer 2, same thing to the last layer. And what I want to see after training the model, I want to see actually the weight that has been the weight of the report. So basically I will be having a report here, here, and here, and each one will be having a weight. After training the model, I will analyze the weights themselves so that I can see which report has been used most than others. Basically, I would like to get something like this. So we have 12 layers, and these are the weights, like going from 0 to 1. 0 is the blue and 1 is the red. And basically what I want to get something like this. I want to get, okay, the report number 4 coming from transformer number 4, it's like hugely used compared with transformer number 19, like 12. It's not used at all. So that can give me an information or like kind of point of view so that I can just, instead of using all the reports, I can just limit myself to 6 reports and that's it. But let's imagine that we did that using training only on one data. We need to make sure that these kind of findings that we will find generalize across different SSL models. So basically, we have different SSL models, as I showed in the beginning, Wave2Vec, WaveLM, Hubert, and all of that. If I limit to only use 6 layers, it should be consistent across all these SSL models. Second thing, it shouldn't be dependent on the backend. As we said, the expert that we will be using. So the expert needs to read the report. Any SSL model you give it to him, like for example, if I give Wave2Vec or WaveLM or Hubert, it should act similarly. So the expert shouldn't be biased to the report. And the third thing, what about different types of defects? Because we have different types of defects. We have the music, for example, defect, environment defect, partial defect. So we need to make sure that the report that we'll be constructing, the small report, it's consistent across different defects. Okay, so to do that, so to answer these questions, we did a huge experiment. And basically the experiment, we analyzed different SSL models, basically 6 SSL models: Wave2Vec small, Wave2Vec large, Hubert small, Hubert large, WaveLM small, WaveLM large. Let's get back to the point. Why do we need all these SSL models? So that if we decide that we will be using only 6 reports, it should be consistent across all of them. Second thing is the expert, the backend that will see the report and decide whether it's real or fake. Instead of using only one backend, we use 2 backends so that the analysis can be generalizable. And the third thing is the type of defects. So we use a huge data that has really a variety of defects. Basically, it has like English defects, Chinese defects, partial fakes, multilingual fakes, song fakes, scene fakes, like different fakes, different like speech or audio defects. So that's the type of report that we will be constructing should generalize to all of them. Let's see what we found out. So if you remember, these are the weights of the reports from different SSL models. I will be explaining the full heat map. So here we have different SSL models. We said, so Wave2Vec small, WaveLM small, and Hubert small. These are their layers. So basically the reports that we will be getting from each layer. And this assist and FFN are 2 different experts. 2 different experts that see the report and decide which one is useful. So we can clearly see across all these SSL models and across all these like experts, if we say, we can see that the huge weight of the report is given to the first, like to the acoustic one. The first, second, third, fourth, fifth maybe 6 as well sometimes. So, but basically only that. So only 6 reports are sufficient to make the decision. No need for the 10th or to 11, 12. So basically that gives us an idea that we don't need the full SSL model. We need just a subpart of it so that we can make the decision. This is for small models. Let's see if this is consistent with large models. For the large models, we can see clearly similar trend. Basically, if we see the average, we can see that using the report, using only 8 layers, that's largely sufficient. 10 layers, that's hugely sufficient. But using 21, 22, 22, 23, 24 layer, that's not really sufficient. Like giving the report from the layer 23rd or 24th doesn't add anything, doesn't have any additional value. So from these two tables, what we get? We get that the most useful reports are the reports coming from the lower layers, are the acoustic reports. So the report that has information about intonation, F0, F1, speaker embedding as well, but not the features or the reports that has information about the phoneme embedding, the word, and all of this extra information. So what we need to do now, so we know this thing. What actually we need to do is we need to go to this SSL model and remove all the reports coming from these upper layers. So basically what we will be doing, we have here 24 layers. Okay, so 24 reports. Instead of having 24 reports, I don't want any more these 24 reports. I want only 6 or 10 or like 16 reports at max. So I will reduce the number of reports and retrain the system and see if it will give me similar results or not. And that will put us to the last experiment and the last findings. So basically here, we repeated the same experiment. I will explain the table. So basically here we have the backends, different backends that we tried. And here the different experts that we tried. And here the layers, number of layers, like remember, the layers are the reports. So basically here we limited to only using 2 reports, 4 reports, 6 reports, or the full reports. Like we've done the experiments across different data sets to see whether using lower reports is sufficient or not. So basically what we've seen is that the reduced layers, okay, so reducing the reports to only 4 reports to 6 reports is giving the best results, as you can see here. So here we have the results. The best results is using 4 or 6. And here 2 layers is giving the best. Like it's quite consistent. And even though, like for example, sometimes where using the full report is like more useful, we can see that the results are very close by. So here we have like 9.99 using only 6 reports compared with 9.26 using the full report. So basically that's give us an idea about like limiting the number of reports. That should be sufficient. No need for using the full SSL model, the full 2 billion model. We can limit it to only maybe 100 of millions. That should be largely sufficient for defect detection. And the similar trend has been seen in large models. So large models, we limited as well, and we've seen similar trend. So for example, limiting to 8 reports instead of 24, we can see really good results with 8, like as can be seen here. Here as well, like using 12 reports is very useful. Assist as well, like different models. So basically, like in the lecture, like the lecture today, what we've seen that SSL models are very useful for the defect detection task. So they give a full and huge report that can be used by an expert AI model, and this AI model can decide whether the input is fake or real. But basically, we don't need the full report because these models are very huge, can go from 90 million to 2 billions, and we need like kind of efficiency. So what we've done, we analyzed the reports given by different layers, and we've seen that using the lower layers, lower reports, it's the most useful part for the defect detection. And what we've done, we verified that actually limiting to these lower layers, it's sufficient. So that was the talk for today, and I hope it was clear, and I'm open to the question now.